Hello, this is Guillermo Campitelli, and in this video I'm going to explain the first part of model comparison, only the maximum likelihood approach, in a case in which a nominal variable affects another nominal variable, and we've already presented the cognitive reflection test case study, and we're going to continue with that study, but now with model comparison. And model comparison, I'm going to spend a lot of time with the maximum likelihood approach because it's quite complicated in when the two variables are nominal. Okay, so I'm not going to show you the way of doing it with software because I use R, so you're not going to actually do it, but you may encounter these models in the literature, and you will see likelihoods, log likelihoods, odds ratios, sort of measures which you may not understand. So the goal of this course is to understand what we are doing, and that's why I'm going to spend quite a lot of time explaining where do the values that we get from the output of software come from. We are going to use multinomial models for model comparison, and we're going to compare a null model, model 0, in which the type of response is not affected by the type of problem. So basically, the differences we find are due to unknown variables. And we compare that to model 1, which is the model that we are interested in, that says that the type of problem does affect the type of response. Okay, so why we are using multinomial and not a linear model? Well, because linear model requires that the dependent variable type of response is a numerical, and in this case we don't have a numerical variable, we've got a nominal variable, and things are complicated because this one is also nominal. So we cannot use a linear model, we cannot use a logistic model. That logistic model is used when the type of response is nominal, but it has two possible values only, 0 and 1, so some binary variable. And so multinomial is when the type of the dependent variable is a nominal variable and has more than two possibilities. So now, the output you will get for model 0, if you use any software, is these two values, 1.619 and 1.374. And I want to show you where those numbers come from, what do they mean, and also I momentarily complicated things by presenting 9 values. And the reason is of doing that is that I want to compare those values with model 1, which has 6 values. So we are going to have 6 values in model 1 and only 2 values in model 0. And I want to explain why is that the case and what those numbers mean. Okay, so let's start by saying that we cannot use, because the response variable or the dependent variable is a nominal, we cannot use a linear model. So instead we use a linear combination of the independent variables to make a prediction of log odds. Okay, now what are log odds? Okay, we are going to predict the logarithm, the natural logarithm, ln is the natural logarithm, and I'm going to explain that a bit later, between two probabilities. So, sorry, between the ratio, so the natural logarithm of the ratio of two probabilities. We are always going to use one of the types of responses as a reference value of the dependent variable. So we are going to use other in this case as the reference. So when we calculate these log odds, it's always, when we are talking about correct, would be the logarithm of the ratio of correct over the probability of correct over the probability of other. And when we are talking about intuitive, it would be the logarithm of the ratio between probability of intuitive and probability of other. And when we get this so far, we got these two numbers and we don't get that number. But we can think of that number as being 0, and that's why it's not reported, because it would be the logarithm of the probability of other over the probability of other, and the probability of other over the probability of other, because they are the same value, that is 1, and the logarithm of 1 is 0. So basically what does these 1.619 and 1.374 mean? Okay, so they mean that our prediction for the original, for the blurred, and for the mathematical, it would be the same, because in model 0 we are claiming that the type of problem doesn't have any effect on the type of response. So if there is no effect of type of problem on type of response, then the prediction would be the same for the three problems. And that's why we've got only two values. Okay? So let's go convert this value 1.619 and 1.374 into odds. So we've got log odds and we want to convert that into odds. And I'm going to come back to the log odds. Why do we want log odds? Okay, so basically we do the reverse. When we obtain 1.619 by obtaining the logarithm of the ratio of two probabilities. Okay, if we exponentiate that number 1.619, we obtain the ratio of those two probabilities. Okay, so the ratio of those two probabilities of correct over other is 5.047, and the ratio of intuitive over other is 3.951, and obviously the ratio of other, probability of other over the probability of other, should be 1 because it's the same number. Okay, so ratio means if it is higher than 1, means that the probability of correct is higher than the probability of other. If it is 1, like here, it means that the two probabilities are the same value. This could be lower than 1, meaning that the probability of correct is lower than the probability of other. Okay? Now, when we transform these odds that can take values from 0 to plus infinity into the logarithm of the odds, we transform this variable in one that is not bounded by 0, but bounded by minus infinity. How is that? Okay, so the logarithm of 1 is 0. if any of these values is less than 1, then we are going to, the logarithms are negative numbers. And values that are more than 1, the logarithm will be positive numbers. Okay, so basically that is the transformation. We want to obtain a log odds which are bounded from minus infinity to infinity. Why is that? Well, because if you want to do a linear model, the linear model will give you values that are from minus infinity to infinity. Typically, the distribution we use for predicting the possible values of data is the normal distribution, and you know that the normal distribution is bounded from minus infinity to plus infinity. So if we want to get into a linear combination of independent variables, then we need to transform to log odds, which is it will transform things into a variable that ranges from minus infinity to infinity. Okay, so I'm going to move one slide further and show where these odds 5.047 and 3.951 come from. And they come from the probabilities. And probabilities, they are bounded from 0 to 1. And here it's we have the probability of correct, the probability of intuitive, and the probability of other. Where these probabilities come from? Well, these are the average probabilities for other over the three problems: original, blurred, and mathematical. The same for intuitive. 0.395 is the average probability of intuitive over the three problems, and 0.505 is the average probability of correct answers over the three problems. So those are those values. As what you can see is that if you do 0.395 divided by 0.1, that gives you 3.951, which tells you that probability of observing an intuitive answer is 3.95 times higher than observing another answer. And the probability of observing a correct answer is 5.047 times higher than observing another answer. Now, again, we've got the same values for the three rows, and that's because we are not taking into account the type of problem. We make the same prediction for all the problems. Why we are doing that? Because the model is a null model that tells us that there is no effect. When we go to model 1, we want to see whether model 1 is better than this model 0 that says that there is no effect. Okay, so now I'm going to go the other way around. I'm going to start from the probabilities to the log odds. So basically we start with the average probabilities over all the problems, and these are the values 0.1, 0.395 and 0.505, and we obtain the odds. So we obtain the ratio of this one over this one and this one over this one, and I'm going to come back now to the previous slide, and this is what we obtain, the odds: 5.047, 3.951, and if we do the probability of over the same probability, obviously that would be 1. And then we obtain the logarithm of those values and gives us that. And that's the output that we get. So that's why it's important to understand where do these numbers come from, because we get that output and we don't know what it means. It doesn't give us any idea what this could be. Okay, so and now I'm advancing to the next slide that you've seen just now, and the last part gives us the measurements of the fitness of the model 0. So we've got the likelihood, which is minus 197.869, the deviance, which is minus 2 times the likelihood, and the AIC, which takes into account the deviance but then penalizes for the number of parameters. Here we've got 2 parameters, so the penalty goes, the AIC goes from 395.7 to 399.7. Okay, so how do we come up with these likelihood? Okay, so in this way, given this model, for each participant, we say that the probability that observing a correct answer in that this participant is 0.505. The probability of observing an intuitive answer is 0.395. And the probability of observing another answer is 0.100. What the actual data is that in the original problem, 35 were correct, 30 intuitive, and 5 other. For blurred it's 34, 33, 3, and for mathematical 37, 20, 13. Now, for these 35 people in the original problem that got the correct answer, the likelihood was 0.0505 to observe that response, correct response. And because using the multiplication, the product rule of probability theory that we've seen in previous videos, then we multiply 35 times, 0.505 35 times, or we elevate to the power of 35. For the 30 participants, the likelihood of observing the intuitive answer was a bit lower than this. It was 0.395. So for this model, the likelihood of observing this data for each of these participants was 0.395, and because we observe it 30 times, we multiply 0.395 30 times. And for the 5 participants that showed another answer for this model, the likelihood of observing that answer was 0.1. And so we are going to multiply 0.1 5 times, or to elevate to the power of 5. And we do the same for each of these cells. We get the probability that the model gave us to that cell, and we elevate that to the power of the number of times this answer was actually observed in our sample. So by doing this, we get a we are going to obtain a very small number, because if multiplying all these values less than 1, we're going to get a very small value. When we obtain the logarithm of that, that's the likelihood, minus 197.8. We multiply the likelihood by minus 2, and we obtain these. We penalize for parameters, and this is the AIC of the model. So now we are looking for model 1. It has to have an AIC which is lower than this one to show that the type of problem would change the distribution of responses in the cognitive reflection test. Okay, so let's see model 1. And model 1, the values that we get as output in the software, they're even more complicated. They're not very intuitive at all. Okay, so remember that for model 0, we only had 2 values. And now we've got another complication. That the explanation I was given was all good, but we didn't take into account the independent variable, because we said that the independent variable didn't affect the dependent variable. Now in model 1, we have to take into account the independent variable, and the independent variable happens to be nominal as well. So we have to also have a reference value of the independent variable. And we are going to take original as the reference value. So other is the reference value of the dependent variable, and original is the reference value of the independent variable. Okay? So what's 1.946 and 1.792? Well, that's exactly the same as in model 0. That's the log likelihood of correct over other, and that's the log likelihood of intuitive over other. Now, then you get these values in the output: 0.482 and 0.606 for blurred, incorrect and intuitive respectively, and in mathematical you would get -0.900 and -1.361. And what does this mean? Very difficult to explain, but I will try to do that. Basically, it means that the log likelihood of correct over other in blurred is 0.482 more than the one for original. So if in original the log likelihood of correct over other was 1.946, we have to add 0.482 and it gives us that, but this value you will never see in the output of the statistical software. But you need to, you just can add this value plus this value and you obtain that. So basically the log likelihood would be 2.428 of blurred over other, of correct over other in the blurred problem. Same with intuitive. Intuitive, for the original problem, the log likelihood of intuitive over other was 1.792. Now, that's the output of the software. What does it mean? It means that we have to add 1.792 plus 0.606 to get the log likelihood of the intuitive over other. So these two values are the increase in log likelihood that happens from moving from original to blurred. Now, then for mathematical, the software gives us -0.9 and -1.3. And what that means is that the log likelihood of correct over other is lower in mathematical in comparison to original. So if we actually do it, instead of being 1.946, it would be 1.046. Same with intuitive. So the log likelihood would be lower in mathematical. So the log likelihood intuitive over other, instead of being 1.792, it would be 1.361 less, which is 0.431. So the log likelihood of intuitive over other is 0.431. Okay, so now we can translate those values into odds. Those values here that the software gives you, you cannot transform that one into odds. Yeah, so that's why I wanted to explain this. The output you get is very, very difficult to interpret. Okay, so if we exponentiate, because in order to undo the logarithm, you use exponentiation. So this 1.946 transforms into 7. This 2.428 transforms into 11, and this 1.046 transforms into 2.846. Same with this, 1.792 transforms into 6, 2398 transforms into 11, and 0.431 transforms into 1.539. And what are those numbers? Okay, these are the odds. That means that the probability of correct in the original problem is 7 times higher than the probability of other. Probability of intuitive is 6 times higher than the probability of other. In blurred, the probability of correct is 11 times higher than other, and the probability of intuitive is 11 times higher than other. And in mathematical, the probability of correct is only 2.8 times higher than other, and the probability of intuitive is only 1.5 times higher than other. And by transforming this into actual probabilities, we obtain the next slide, which is that recovers the actual data. So the actual data is these values, which we obtain by doing the exponentiation first of the logarithms and then transforming these odds into actual probabilities. Okay, so then after all these transformations, these are the predictions of the model. So we can go to the table in which we are going to see the likelihood, the expected probability in the original problem for correct is 0.5, for intuitive is 0.429, and for other is 0.071. Unlike model 1, these values will change in the blurred problem and in the mathematical problem, so they are not the same as in model 0. And basically, because there were 35 people in which we observed correct, for those the probability of observed the data that they generated was 0.5, so we have to multiply those 35 times. For these 30 people, the probability of their answer was 0.4, the likelihood of their answer was 0.429, so we multiply these 30 times. And for the 5 that obtained other, the likelihood was much smaller, 0.071. We have to multiply that 5 times. We multiplied everything, and then we obtain the logarithm of that, and that's this value, minus 192.154. Then we obtain the deviance by multiplying these by minus 2. And then AIC, we need we have 6 parameters. I'm going to return to the previous slide. And you can see that we've got 1, 2, 3, 4, 5, 6. These ones are not estimated, they are fixed. So the AIC, the deviance was 384, but we penalize and we get 396.3. How does this compare with the model 0? So for model 0, the AIC was 399.7, so the difference is a bit in favor of model 1, but not very important difference. So the evidence for model 1 over model 0 is rather small. It's still a bit more likely than model 0, but not too much more. So 399.7 versus 396.3. So 3.4 points of AIC difference, which is a very small evidence in favor of model 1. Okay, so that's the explanation of the maximum likelihood approach. So in model comparison, for the Bayesian approach, we are not going to use it in this case, because the comparison between the null model and the model that we are interested in, it would be the same as doing null hypothesis testing, because the null model is equivalent to null hypothesis. So we are going to see that in hypothesis testing.